Welcome to our webinar on transfer methods, some basics on blotting techniques. This should be an overview over different methods, and maybe there is the one or other thing you haven't known so far. I also would be grateful if you would ask questions in the end of the presentation. Yeah, let us start right away. So what is blotting? We understand under blotting the transfer of macromolecules onto an immobilizing membrane. So the macromolecules can be DNA fragments, RNA fragments, or proteins which will stick to these membranes that we use here. There are two types of blotting. One is without any pre-separation. I will show you a slide on this very soon. But most of the blotting methods are performed after electrophoretic separation of the nucleic acids or the proteins, and then you have the macromolecules on the surface of a membrane, no longer in the gel. And so then you can perform hybridization in the case of nucleic acids, or immunodetection or similar detection methods for proteins. Here you have some apparatus examples for transferring proteins in an organized way onto a membrane for slot blots or dot blots. Here these are the systems. And here you see a typical result for a dot blot after detection of the blotted macromolecules. But mostly, as I said, we are using electrophoretic separation. And there, all this started in the year 1975 with the so-called Southern blotting. That was a method introduced by at Southern, a DNA transfer from agarose gels after separation onto nitrocellulose membranes for hybridization. I will show you a separate slide just describing this technique in more detail. 2 years later was a paper on Northern blotting, but that was not invented by Mr. Northern. It was just to the honor of Ed Southern. They called it Northern blotting. It was just an RNA transfer and further analysis, also from agarose gels. Again, 2 years later, in 1979, was Mr. Taubin and his group. They introduced the protein transfer with immuno or with affinity detection. For glycoproteins, you can, for instance, perform affinity detection with lectins, and they called it the Western blotting technique. I've never heard about an Eastern blotting technique. There were some rumors about diffusion blotting, but there was, for a certain while, far Western blotting. I haven't heard about this method anymore in the last couple of years, but what it described was a protein transfer for probing protein-protein interactions on a blotting membrane, so without immuno or affinity detection. The transfer methods used can be diffusion blotting. Diffusion blotting means just placing a blotting membrane, immobilizing membrane on the surface of a gel and let the separated fractions diffuse onto the membranes. It's not very efficient, but in some cases just enough. Much better is capillary blotting, which was introduced by Ed Southern. I will show a slide, then you know exactly how it works. And there is also vacuum blotting. These two methods have mainly be used for transferring nucleic acids, RNA and DNA molecules. And for proteins, preferably electrophoretic blotting is used. So here for the transfer of nucleic acids, on the left you see a capillary blotting setup. You have a support on this. You have a filter paper which sucks the buffer out of a tank or out of a tray, the blotting buffer. And on top of this you have an agarose gel on top of the agarose gel the blotting membrane, nitrocellulose or nylon membranes in these cases, and on top of it a stack of dry blotting papers, and on the top of this a larger stack of dry paper towels, and then a glass plate and a weight. And so the dry paper sucks the fluid, the liquid up, and so the liquid has a motion into this direction, and this motion, it takes the separated molecules, the nucleic acid molecules with it onto the blotting membrane where they stick on the surface. The other way around is the vacuum blotter. You just have a buffer, a gel, and the membrane, and something like a microgrid, and then you suck the buffer with a vacuum pump, and this way you get a transfer of the molecules onto the blotting membrane. So here, very shortly, how sudden blotting is performed. So you digest the DNA with restriction enzymes, and you want to look for a gene of interest. So you separate the fragments in an agarose gel, submarine technique usually. And then here you see a small setup of a capillary blot on nitrocellulose. Then you take the blotting membrane, you submerge it in a solution having radioactively labeled probes in solution, and for a certain while, and then you expose the blotting membrane either on an X-ray film, or you place it into a camera system and detect the gene of interest in this way. So that's definitely, this is sudden blotting. So for protein separations, as I already said, mostly electrophoretic transfer method is used. So, and mostly we are working here with polyacrylamide gels. There are some exceptions. For instance, when you have to separate very large molecules like oligomers of von Willebrand factor, then polyacrylamide gel has too small pores, and people prefer to run, for instance, STS electrophoresis in agarose gels and transfer the von Willebrand factor oligomers from an agarose gel onto such a membrane. There are also cases where electrophoretic transfer might not be the optimum. I will talk about this in a little bit later in some separate slides. So now the membrane has a high affinity to macromolecules. They stick to it. Before you probe with another macromolecule, like with the primary antibodies for detecting your specific proteins, you have to block the background, the non-used background. And the blocking reagent you use is some other macromolecules which do not interfere with the detection procedure that you intend. So, for instance, bovine serum albumin, or I will show you a list of often used blocking reagents later on. And now you can submerge your membrane in a solution of primary antibodies. The primary antibodies will recognize the antigen you are looking for, and then you use a secondary antibody which recognizes the primary antibody, and the secondary antibody has usually a detection system bound to it. And for instance, there's a fluorescent detection or chemiluminescence, which give you very, very sensitive results, very sensitive detection. Here's an example. On a very old slide I have. You see a sample separated in STS gel. In this lane here, 100 micrograms was loaded. The gel was stained with chromacy blue as a general staining. But when you perform blotting with the same sample, you just can use much, much less sample. Just 1 microgram is loaded here in this lane, and there was a chemiluminescence detection of E. coli GRO-L protein. You see the sensitivity is very high and the specificity is very high. But I have to admit that the specificity depends on the quality of the primary antibodies. So if the primary antibodies are not very good, so to say, very specific, then you won't have a single band, you won't have more bands. This is usually the reason why sometimes people have more than one band after blotting. Preferably, we are using denaturing electrophoretic separations prior to blotting because, and I have written this here, denatured proteins are in ideal condition for immunoblotting because then the antibody can detect the epitope. Proteins have quite often, or always, tertiary and secondary or even quaternary structures. So that could cause a problem for the antibodies to have access to the epitopes. But STS electrophoresis is mostly used because of several reasons. The STS solubilizes almost all proteins, so it's a very good detergent to get proteins into solution. And as it covers the proteins, the individual charges are covered, so every protein is negatively charged and all proteins migrate into the same in one direction. So you have all proteins in one separation, also the basic ones, not only the acidic ones. You can estimate the molecular sizes, that gives you an additional information on the protein, and as I said, denatured proteins are better for immunodetection. If you have to perform isoelectric focusing, then you can do that in presence of 7 molar urea, and then also here you get an opening up of the tertiary structures and the stretching out of the polypeptides and easier access to the epitopes. What is very useful after STS electrophoresis is to co-run markers which are pre-stained. Here you see a few examples which are available from Serva, and these stained markers not only show you an estimation of the molecular sizes, but also give you an indication on the transfer efficiency. So you can really see if all the proteins, also the large ones, because the large proteins very often cause some troubles for transfer because they don't migrate so fast in a gel onto the membrane. You can check how good was the transfer of the proteins, how quantitative. I have to say that the blotting transfer is never 100% quantitative, so quantitative tests with blotting is always a problem. Membrane choices. So in the beginning, as I already said, mainly nitrocelluloses were used and at 0.45, mainly for blotting after isoelectric focusing, and 0.2 micrometer pore diameters after STS electrophoresis. But the nitrocellulose is a little bit fragile. There was a trend going to PVDF. PVDF membranes invented in the company Millipore a couple of years ago are also available in different pore diameters, but they have a much better mechanical strength and better binding, higher binding capacity. But they are very hydrophobic, so you have to wetten them first in alcohol, methanol, ethanol, or isopropanol. So why don't you always use PVDF? And there's one reason to use nitrocellulose is usually it's cheaper, yeah, but also it binds smaller proteins and peptides more efficiently than PVDF. So that's one of the reasons to use nitrocellulose, and now you have also supported nitrocellulose on the market for better mechanical strength. For isoelectric focusing, you have to bear in mind of one fact. In isoelectric focusing, you are driving the proteins to their isoelectric point. That means the proteins at the isoelectric points have a net charge of 0. And for transfer, an electrophoretic transfer, you need charges on your molecules. So there are some reasons to use a different transfer method. There are possibilities to transfer electrophoretically, but it's a little bit tricky sometimes. So there are more and more people switching over to pressure blotting, like on a PVDF membrane, So the gel is equilibrated for a certain while in blotting buffer, and also the membrane in alcohol, then in blotting buffer. And then you see a setup here. It's almost similar setup like the capillary blotting. There's just no suction out of a buffer from a buffer tank. It's just using the weight and the dry paper to suck out the proteins from the gel. All this is based on a paper by also Harry Talwin, so the one who introduced the Western blotting, but he and his colleagues published a paper in 2001 showing that the transfer out of a isoelectric focusing gel is better with brusher blotting. For electrotransfer, first tanks were used. The tanks had a grid with platinum electrodes on the two side walls, and you insert a cassette, a grid cassette containing the blot sandwich, which is built up by the gel, the membrane, and some stacks of filter paper soaked in the blotting buffer. And you transfer usually from cathode into anodal direction when you use a basic buffer system. A couple of years later, namely in 1984, the semi-dry blotting was introduced. This does not need any more the large volumes of buffer. You just have plate electrodes, graphite or titanium. There are new material on the market also here. And here you only need filter paper soaked in the buffer and not the big buffer volume. Here, these systems you can cool. These systems are usually not cooled. There's a third thing, is semi-wet blotting. Here you have the blotting sandwich in a closed cassette, and you introduce this closed cassette into a blotting buffer tank, in the gel electrophoresis buffer tank. So there you have a possibility to remove the Joule heat in a heat sink, so by having buffer or water in the tank. I will show you some more details in a moment. For tank blotting, mostly the so-called Talwin buffer is used to twist glycine and methanol, or as we know nowadays, you can replace the methanol by ethanol or isopropanol. The reason to use an alcohol, there are two reasons. First of all, nitrocellulose binds better in presence of about 20% alcohol. Secondly, gels, when they are removed from the cassette or from the support film, start to swell. And in presence of alcohol, the gels are not swelling, because when gels swell during the blotting procedure, the bands are not sharp anymore. You have blurred bands. Sometimes people put SES in the blotting buffer for more charges, negative charges on the molecules, or particularly when they had negative native gels in the separation. For a large tank apparatus, you usually need a power supply for 1 to, I would even say, 2 amperes for 1 to 2 hours or longer. If you need longer transfers for larger molecules, then you should have a cooling system built in. Some people have not been happy with the transfer effectiveness of the Talwin buffer, so they prefer the cups buffer. They titrate the cups with sodium hydroxide to pH 9.9. Glycoproteins transfer better in a sodium borate buffer because the borate sticks to the sugar moieties and adds additional negative charges to the glycoproteins for efficient transfer. And if you want to electrophoretically transfer proteins from isoelectric focusing gels, the preferred buffer is acetic acid, 0.7% usually, but take care. In this case, you transfer into the opposite direction, into the cathodal direction, because it's an acidic buffer and everything is positively charged there. Here you see a typical blotting tank. There are the grids carrying the electrode wires on the both walls, and inserted are here some cassettes having the blot sandwich built in. Setup these cassettes, you have to be very careful that you don't catch air bubbles in between. So you set up the cassette in under the surface of the buffer, and be careful. It's really dangerous. If there are air bubbles in, the air bubbles interrupt the transfer. So in these areas, you won't get any proteins transferred. In semi-dry blotting, in reality, people always use a weight on the system in practice, because then they avoid a building up of electrolysis gases. You know, electrophoresis and also electric transfer and blotting is causing the build-up of electrolysis gas, oxygen and hydrogen on the anode, oxygen, ions on the cathode. And this can cause building up of cushions, gas cushions, and then you won't have a good transfer anymore. If you have a weight on top of it, the gas is moved out sideways, and you don't have this buildup of gas cushions. Here you see a typical system for semi-dry blotting, which is also available from Serva. It's built by the Höver company. The model I show you here has an inbuilt power supply, but you can have also a cheaper model, same setup, just not containing a power supply. If you have already a power supply with high ampere, you can use it. And don't forget to put the weight onto it when you transfer. The very efficient buffer has been introduced by Mr. Kisi Andersen, who was the one who introduced also the semi-dry blotting, and he took advantage of this technique, because here you can use a more efficient transfer, and you can avoid through blotting of small molecules, because you have a high concentration of tris here. The tris will go in this direction. The beginning is a low concentration of tris. You have a high field strength, so the proteins are moving quite fast electrophoretically, but with the time you have a higher conductivity. That means the field strength will drop and the proteins migrate slower. So with this you can avoid through blotting of some small proteins. And a discontinuous system, epsilon aminocaproic acid on this side, helps you to move the proteins almost at the same speed. In the original paper by Kisi Andersen, here also 25 millimole tris is used in this buffer. I have done it always without it, and I have found I got better results without tris buffer here, because tris is anyhow migrating into this direction, and so you, I have found I got a better transfer without the tris in the cathodal buffer. What is better, semi-dry or tank blotting? There was a paper, I show you the reference here, by Tovai and Baldo many years ago, already in 1987, systematically comparing semi-dry blotting versus tank blotting. And here are the facts. Semi-dry transfer is much faster, usually only 40 minutes. Here they wrote 1 to 2 hours. You need less buffer, simple to prepare, minimal waste, and you get a more even transfer. Tanks are more flexible. You can vary the time and the voltage. You can cool them. And what people have seen is a more quantitative approach, so more efficient transfer. You can choose. Here is again the semi-wet blotting setup shown. And here is a real system for this. So this is this cassette where you set up the semi-dry blot, and then you insert it into the tank. And this tank is a electrophoresis, the tank of an electrophoresis chamber, which can be used for the separation, and then you can also perform blotting in the same chamber. And here you put water in, where you have a heat sink to remove Joule heat, at least partly, from the blot sand. What can you do when the gel is covalently bound to a film support? Particularly useful for large and very thin gels, also for very soft gels like isoelectric focusing gels. When you have a film support, is much better. Avoids breaking of the gel and swelling of the gel. But for blotting, this film is in the way, so it does not transfer the ions. So you have to remove it. You can use such an instrument. We call it a gel remover. It's available also from Serva. And here in this case you see a 2D electrophoresis gel. This is the stacking gel area. It's on a film support, and it's placed on a bent surface. And then, with the help of a wire, formerly people used a wire. Nowadays we have found the fishing line material is much better, thinner, stronger than wires, does not break so evenly, is pulled between the gel and the film support. And this is a very efficient way to remove the gel. So the protocol you are following is first placing the gel together with the film support into the blotting buffer containing methanol or other alcohol, usually 20%, then placing it on the system, on the gel remover. Then here is the cutting wire, even we call it a cutting wire even when it's a fishing line, and pull it over the edge of the stacking gel, because you won't blot anything from the stacking gel. The stacking gel usually does not contain any protein anymore. It is a soft gel, so you won't like that. So you may hook it up here, and there is a lever. You pull it straight, so you have a straight pulling of the wire, and then you pull the wire through. You can put already the dry nitrocellulose on the gel, and the gel will stick to the nitrocellulose. With two hands you pull the wire between the gel and the film support. Then you can take the gel off together with the wire. So the film support does not contain any gel anymore, only the stacking gel here. And now you can place this into the blot sandwich. So it makes life easier, particularly when you have large gels and thin gels and soft gels. That works quite well with the nitrocellulose, but when you want to use PVDF, you have to pre-soak the PVDF in alcohol first, and then it will not stick to the gel. So in this case, you do it in a different way. You pull through between the film backing and the gel with a wire, then you take this together, place it on the bench, put a PVDF membrane just on the area of the separation gel, then you flip it around, and with a spatula you can now remove the film support together with the stacking gel from the separation gel. The separation gel is lying now on the PVDF membrane. If you have folds, and very often this causes folds here, you just place it together into the buffer bath or methanol bath, and then you can move out the folds and place the sandwich into the blotting setup. Okay, a few more things. Just a few comments on blocking reagents. So for nucleic acids, there was the famous Denhart's buffer. It's a combination of many things, a cocktail of BSA, Thicol, PVP, EDTA, sodium chloride, tris chloride, and also some heterologous DNA to block the background. For proteins, there are several different suggestions, because proteins react more specifically. It might be okay, you use BSA. Some people preferred casein fragments because they have different sizes of the molecules, so they block more efficiently and does not interfere with most of the detection procedures. Or skim milk powder, a lot use between 20, or also fish gelatin. Some companies who sell very sensitive detection systems, chemiluminescence detection reactions, they also provide special cocktails for blocking, because one of the reasons why you could get dark background in a high sensitive detection method could be that you don't have efficient enough blocking. So this is going together with a very sensitive detection techniques. So what detection techniques are used? So in the beginning, people used radioactive labeled probes, fluorescent labeled probes, or still possible, general immunossaying. Mostly, however, they were first staining the blood with amido black. Soon it was found out that Ponceau S is superior because Ponceau S is a reversible stain, very efficient. So you first see the red spots or bands on the blood membrane. You can take an image of that, and then can, by washing in water, remove the Ponceau S completely. Some people stain with Kumasi blue, but this is not reversible. Indian ink is also not reversible, but it does not interfere with immunodetection. And there was also the colloidal gold from the company Janssen, this 80s and 90s of the last century. I don't know how often it's used anymore, but it was very frequently used in the past. Mostly people use enzyme-coupled secondary antibodies. One choice is alkaline phosphatase, the other one is horseradish peroxidase. And you can amplify the signal with a combination of avidine or streptavidine and biotin, so you produce a bigger amount of protein on the position of the blotted antigen, and then you combine that with horseradish or with alkaline phosphatase detection. And finally, chemiluminescence. This is by far the most sensitive detection techniques, usually also based on horseradish peroxidase coupled secondary antibodies. Here is an example. There's a blood membrane. Here you have the primary antibody. Here is the secondary antibodies coupled to horseradish peroxidase, and then you have a chemiluminescence substrate bound to the horseradish peroxidase, which on the reaction produces light. So you can expose the blood to an imager. Formerly people used X-ray films. Nowadays almost everybody has a CCD camera imager because it is more efficient, and so you can use very long exposure times. In this way you can collect a lot of the light and get very high sensitivity photons. In the Serva company, we have 4 different chemiluminescence reaction kits. They have been introduced about 2 years ago, and they're very efficient, very sensitive, and very easy to use. And there is the Polaris substrate kit. It has very good sensitivity in the low up to the low picogram limit, and the emission time is up to 6 hours. There's a more sensitive. This is the EOS, very high sensitivity. It goes down to the high femtogram limit, and you have very long emission time, up to 12 hours. The next, even more sensitive, the EOS Ultra, in the low femtogram area, limit of detection, and also very long emission times, up to 18 hours. And the most sensitive and the best, and of course also unfortunately the most expensive one, is the Helios with horseradish peroxidase. It is also in the low femtogram limit of detection, but also with a shorter emission time, up to 8 hours. They get the same sensitivity like with this one. One specific blotting method I want to show you in the very end, the so-called double Immuno Blotting after isoelectric focusing. This method has been introduced by Madame Lasnay from France because she's working in anti-doping laboratory, Nevada laboratory, and there they want to detect artificial epopoietin, EPO, short name is EPO, erythropoietin, sorry to say, in sports people. So, and what they test is urine of the sporters, and so these urine samples are taken, and then they are concentrated, then they are cleaned, but they still contain a lot of junk which can cause cross reactions, and then you don't get an appropriate result pattern. So what is done here is isoelectric focusing first in presence of 7 molar urea usually, but also they also perform SDS electrophoresis, but mostly isoelectric focusing. And here with isoelectric focusing, the pressure transfer method has become more and more the method of choice because of the reasons I told you already. So they blot, they transfer all the separated proteins on the blotting membrane. Then the background is blocked. Then they have primary antibodies against EPO, erythropoietin molecules. And now is not directly continued with secondary antibody, but a second blot is performed. So the blotting membrane is placed into an acidic buffer. And you know at pH 3 you can remove, you can open up again the immuno complex. So the antibodies separate from the antigens again at this low pH. So then now you transfer at low pH the antibodies, the detecting the primary antibodies from the first blot onto a second blot. So all the antigens will stay, all the proteins will stay on the first membrane, only the antibodies will come off and will be stuck on the PVDF membrane. Then you perform another blocking procedure. Now you have the secondary antibodies connected to chemiluminescence reactions, and now you can detect with very high specificity and very high sensitivity the bands. And here you see one example which I have received from the WADA laboratory in Kreischer, which is close to Dresden. So there was isoelectric focusing performed, 7 molar urea and a pH gradient 2 to 6. Then the double blot was performed, as I explained, and then with chemiluminescence detection, you can detect, you can see the differences between human EPO and artificial EPO. Yeah, that was the overview over blotting and transfer techniques. If you have any questions, I would be happy to answer them, and I thank you very much for your attention.